Good afternoon to everyone. I'm Laura Carletti and I'm a first-year PhD student at the Scuola Superiore Sant'Anna in Pisa, and this work is in collaboration with the company Medica S.p.A. We divided our work into 5 steps: the clinical need and the presentation of the hardware proposed by Medica, the feasibility test for the creation of the hyperlipemic plasma samples, and the measurement campaign for the database creation. And the main core of our work is the AI algorithm development. Then I present you our results and the future research. These lipidemias are a chronic condition characterized by elevated levels of LDL cholesterol and triglycerides, and they are one of the major risk factors for the onset of cardiovascular disease. And in addition to a correct lifestyle, pharmacological therapy is a fundamental strategy for obtaining recommended therapeutic targets. Lipoprotein apheresis, that is the process of extracorporeal removal of LDL cholesterol and triglycerides, is considered by the ASVA guidelines a last resort option of treatment for individuals with homozygous and heterozygous familial hypercholesterolemia. In the LDL apheresis device that utilize a membrana plasma separation as the initial stage, an important sensor is the blood leak detector, and the commercial sensors was based on the optical absorption. So there is a emitter at a specific wavelength that illuminates the plasma, and a receiver that detects the transmitted radiation. In general, plasma is transparent to the light, so when in blood is present, it absorbs the radiation and leading to a decrease of the transmitted radiation. If this falls below a critical threshold, alarms are triggered to indicate the presence of blood. During the lipoprotein apheresis, the high content of lipemic part of plasma can lead to a decreasing in the amount of transmitted light, so we can have some of false alarm. So the hardware presented by Medica is based on microspectrometers operating with either visible range in 320 to 885 nanometers, and the sensing technology is based on broadband LED and multimodal fiber optics positioned to minimize the distortion introduction from the cylindrical measurement cuvette. And feasibility tests were, we did feasibility tests to establish a protocol for the creation of lipemic plasma samples, and we find four approaches in literature. We use the last one based on the standardized fat solution. In particular, we decided to utilize the soy phospholipids, one of the active ingredients of the intralipid compound, and we obtain they follow these samples, so plasma samples with an increase of turbidity, and we test that this sample have a spectra that is compatible with the behavior of lipemic part of the plasma. So we know from literature that the lipemic part of the plasma has spectra inversely proportional to the wavelength without any specific peaks. So we decided 6 phospholipids concentration, and given a blood threshold of 0.7%, we decided also 6 blood percentage for a total of 36 samples. And from the sensors, we have 2 types of spectra. One, this is the original one that we call non-normalized spectra. And after, we utilize also normalized spectra, that is the original one normalizing according to the physiological solution that we consider as the reference. Each measurement session included the acquisition of 10 measurements, and for each type of samples, we performed 3 measurement sessions for a total of 1,000 antique spectra. and each spectra were normalized by the corresponding LED maximum intensity to ensure consistency. And we manually eliminated outliers, so we have in total 1,067 spectra, and we performed a non-convolutional method for the classification of the samples, and after, to have a better performance, we develop an artificial neural networks. So as a first approach, we consider the non-normalized spectra, and we extract two important features: the area under the blood peaks and the area under the mean peaks, and we represent our spectra in a plane. We can see a separability of the samples with a simple thresholding. On one hand, we have the samples without phospholipids, and the other hand, we have the samples with phospholipids. We search for three regions, so the absence of whole blood, the 0.5% of blood ratio, and the samples with above of 0.7% of blood ratio. And we search and we identify this region through the use of linear SVM for the plasma sample with phospholipids, and with two simple thresholding with for the samples without phospholipids. To have better performance, we pass to the development of artificial neural network. And before this, we perform a pre-processing of the data for the creation of different database with different features. So the first database consider the normalized spectra in a window of interest, and we apply a PCA for a dimensional reduction and a standard scaler. The database number 2 and number 3 consider the area under the blood peak in the case of non-normalized and normalized spectra, and after we apply a min-max scaler. And the database number 4 consider the two feature of the area under the blood peaks and the area under the main peaks of non-normalized spectra. We identify three classification tasks: one binary classification based on the critical threshold of blood percentage of 0.7%, that is the critical threshold LDL apheresis devices, and two multi-class classification, one based on the blood percentage, so 6 classes, and one based on the combination of blood percentage and phospholipids concentration, so 36 classes. In the case of multi-class classification, we applied a one-hot encoding of the labels, and the database were divided in the training, validation, testing set with a split of 70%, 10%, and 20%. And here we can see an example of the artificial neural network for the binary classification applied to the database number 1, so the normalized spectra in the window of interest. And in this case, we apply the L1, L2 regularization to mitigate the risk of overfitting. So results. For binary classification, we achieved good performance in terms of accuracy using each of the database. In the classification task based on the blood percentage, we achieved the good performance in terms of accuracy only using the database number 4. And even in the case of 36 classification class classification, we achieved the high performance with the database number 4. So in summary, the performance in terms of accuracy were reported in the tables. We achieved a good performance in terms of accuracy in all classification tasks, only using the database number 4. So the database number 4 that consider the area under the main peaks and the area under the blood peaks have a very good performance for the binary classification, but also for the classification of the sample based on the blood percentage and of the combination of these two parameters. And the fluctuation of the accuracy from the 6 class and 36 class classification are due to the mutual influence of the phospholipids and blood effect on the spectra. And future research will base on collecting a larger and more diverse dataset to improve the performance of multi-class tasks and to test other methods for dimensional reduction. And the expanding of the database will provide us the opportunity to assessing more powerful convolution models, and also the possibility to assessing the sensor sensitivity to free hemoglobin rather than whole blood percentage in the plasma. So this is the QR code for the paper, and thanks for your attention.